Alrighty, and welcome to the equilibrium practice problems. Questions 1 through 4 first. Questions 1 through 4. The first one's pretty easy. It's kind of a review of equilibrium from last year. We have just a little bit to review here. This is all just setting up the expressions. This should have been pretty easy to handle. The basic idea is that K is always the products concentration divided by the reactants concentration. We only ever include aqueous ions concentration and the concentration of gases in these expressions. So in number 1 here we have ammonia, we have nitrogen, we have hydrogen. This is the product, that's why it's on top. If it has a power, if it has a coefficient, that becomes the power. These are the reactants. They're on bottom. They are being multiplied together, not added together once they get into the equilibrium expression. And then we have a 3 here, so that's why this is cubed, because there's a 3. So we've just set up the expression. And the next one, line kind of got disappeared there. There we go. So we have iodine, chlorine, and iodine monochloride, iodine and chlorine. Important fact here that iodine is solid. Solids do not get included here. If you have a solid, you put a 1 in its place for the expression. So maybe you put a 1 in there. You don't really have to write the 1 in, but you can just keep that in mind. These are both gases, so they're included. Products are iodine monochloride, so it's on top. There's 2 of them, so that's why this is squared. Coefficient's 1 here, so that's a 1. We don't really even need to write that one either, but there we go. And then for the last one, same idea. These are the products. They're on top. That's a 1/2, so that's to the 1/2 power. So really, I guess you're taking a square root. Or you could, in your calculator, just put it to the 1/2 or the 0.5 power later. Whatever O2 is, you could put it to the 0.5 power. Let the calculator handle the math for you. And then that's a reactant, so it goes on the bottom. And so we have these equilibrium expressions that represent the mathematical relationship between the products and the reactants when equilibrium is achieved. What is equilibrium again? Equilibrium is the idea that reactions are reversible. So you see these double-sided arrows. They can go both forward and backward. And when they reach equilibrium, the rate forward and the rate in reverse are equal. That doesn't mean anything other than the rates are equal. Just the rates, the speeds forward and the speed backward are equal. Those could be very slow speeds or very fast speeds. It really doesn't matter. But just that they're equivalent in speed. And because they're equivalent in speed, as this side makes these products are also going to go back and make that. So they end up, the change kind of cancels each other out. And we don't see any more reaction from our external perspective. In the relationship between products and reactants becomes a constant, and that's where K comes from. K stands for constant. So because that value is a constant, it should not change. It doesn't change if you add more moles, because if you add more moles of something, the reaction would no longer be in balance. So if you added more oxygen to this, it wouldn't be at equilibrium. The reaction would go faster in reverse until it got back to K. If you changed the volume, the reaction wouldn't be at equilibrium either, and so it would shift, would go back and forth faster one way than the other. It would shift to the products or the reactants, but in doing so, in changing the volume, when you change the volume, you change the molarities for each of these things, because molarity has a volume component. So when you change the volume of the system, you change the molarity for the NO, the O2, the NO2. All 3 of them just had a molarity change. and then the reaction's not at equilibrium. It's going to shift to get back to K. And the same thing's true with pressure. If you change the pressure, you're going to have more collisions one side versus the other, and it's going to shift to get back to K. The one time, this is I think funny, but the one time K is a constant unless there's a temperature change. Then you have an issue. If you have a temperature change, then it could shift left or right depending on the reaction, and they would have to tell you if it was endo or exothermic to be able to predict what would happen to K. Alright, so there's number one and a whole lot more. Number two, here we're solving for K. We have a dissociation equation, which is to say that this acetic acid is breaking apart into acetate and hydrogen ions. This is a common way of writing acetate. We have CH3COO with a -1. There's a little -1 hiding in there. It has an equilibrium constant. So if this is the equilibrium constant, that's K. All right, and what else did they tell us? The equilibrium concentrations are 0.46 moles of this. There's water. Oh, there's the acetate. There's the volume. We're supposed to find the hydrogen in there. So oftentimes it's good to just, organize your data to go CH3COOH. Here's the reaction. And then let's just write down what data they gave us. They gave us the equilibrium constant. That is the acetic acid. It is 0.46 moles divided by 0.5 liters, because we probably need to know the molarity. So 0.46 divided by 0.5 means our molarity there is 0.92. And then we also have the acetate, 8.1 times 10 to the minus third, divided by 0.5 liters. And I have 0.0162, and we don't know the hydrogen. So this is the question. And so what we did there is we have our expression that equilibrium constant is equal to products. These guys are the products, right? Divided by the reactant, and here's the reactant. Plugged in all the known values, and you can see in this, the way I said this, I didn't actually simplify that. I did the math in my calculator. But if you threw this number in for these two, it should work just fine. In fact, it would probably be easier. But if you do that, you're not allowed to round, are you? No rounding until the end here. And then this is the denominator. This is the one piece we're missing right here, right? We're missing the hydrogen, so that's the unknown value. And we slowly solve for that, and I got the hydrogen is 1.0 times 10 to the minus third. So let's ask a follow-up question. There is not a follow-up question here, but let's go ahead and ask it. What would be the pH of this reaction? pH is really in the future. We wouldn't see a question like this quite yet. But so pH, if you remember from last year, pH is the negative log of hydrogen. And this is one of the equations that's in your equation packet. You don't have to have those pH equations memorized. But so could I take the negative log of 1 times 10 to the minus third and get the measured pH? Well, certainly I would have the negative log of 1 times 10 to the minus third, and the pH would come out as 3. 0.00. There's sig figs in there too, which we don't need to worry about right now. So there could be a follow-up question. And a lot of times in those AP free response questions, it's not the initial setup that gets you to the answer. It's the next step after that. So there's a maybe you have to do an equilibrium expression and solve all these things, and instead of doing, what's the pH, you might have to use that molarity, the moles and the volume, Oh, you know the molarity now, right? You know the molarity. We know the volume. Oh, we could get the moles, couldn't we? And then could we convert moles to mass? Sure we could. That would be a good follow-up question. All right, let's look at the next one. All right, number 3 asks you to compare catalyst, pressure, temperature, and concentration against speed and position. And I already have the answers typed in here. So if you have a catalyst, it speeds up a reaction. It changes the speed at which the reaction reaches equilibrium. 2K. It takes you to K. It takes you to K faster. However, a catalyst does not change K. So it does not alter or change K at all. It just gets you to equilibrium quicker. So the equilibrium position is the same, it's just achieved much faster. All right, what about the next one? How does pressure impact speed? How does pressure impact position? Pressure has a direct relationship. That means if you increase the pressure, you're going to increase the speed, or vice versa, decrease. Because if you increase the pressure, we have to ask yourself, what is pressure? Pressure is collisions between particles which exert forces on each other. Well, in this case, if the particles are colliding more, there's an increase in pressure, you should have the reaction speed up. And if the reactions collide less, there's a decrease in pressure, you should have the reaction slow down. And then the equilibrium position, it really depends on the moles on each side of the reaction. So if we have a reaction and let's just say these are all gases, because gases are impacted gases are impacted by pressure and volume changes. Solids not really impacted by pressure changes. If you change the pressure, you really kind of let the moles be your guide. Or you can do the reverse. Some people think about pressure and they switch it to volume. They say if the pressure is increasing, the pressure is increasing, then the volume would be decreasing. And then they look at this and they say, okay, well, if the pressure is increasing, the volume's decreasing, it would shift to the product side, because this occupies a smaller volume in terms of the moles, is 1 versus 3. If you want to look at that in terms of a collision side, on the product side, you only have 1 particle. On the reactant side, you have 3 particles. And at equilibrium, the rate forward and backward is equal. But if you can get the particles to collide more often, you're going to have more reactions. Well, these particles on the left start to collide with each other more. They're going to have a much greater impact because there's more of them. And whichever one has more tends to react greater to the change. So if you increase the pressure, you have a greater increase on the larger side. So this side with these reactants on it has 3 moles of reactants in terms of the coefficients. This side's going to react faster, or it's going to increase faster than the products. So it would shift to the right as you increase the pressure. But if you decrease the pressure, both sides decrease in terms of the speed. However, as the left side decreases, because there's more moles, it's going to have a much higher impact. And you could even think of it in terms of K or Q, whichever. Let's just write Q. That's probably more appropriate. Say Q is equal to C to the first over A B squared. And as we decrease everything, this has like almost a cube impact, because you have 1 1/3 times 2. It's like a cube impact here, where it's only to the first power there. So any changes in pressure really impact the larger side more. So if you increase it, speed increases faster. If you decrease it, speed decreases faster. Temperature. Temperature has a direct relationship, but it is highly dependent on whether or not the reaction is endo or exothermic in terms of the position. So if you increase the temperature, the speed to reach K would increase. So if there were no products at all, let's just imagine you haven't actually made any products yet, and you increase the speed, these reactants should move at a much faster pace in order to reproduce the missing product. And if you decrease the temperature, these reactants would move slower to achieve K. However, if it's already at equilibrium, how would it shift? Depends on if it's endo or exothermic. So however it shifts for endothermic, it would be the exact opposite for exothermic. So let's take our example here and say that this reaction had an enthalpy of negative 20 kilojoules per mole. That means, since it's negative, that means it is exothermic. It gives away heat heat is given off as A and B's combine to make C. It releases heat, which are now being represented by little squigglies. Let's get those off there. So how the system reacts will depend on what happened to the temperature change. Of course, there's two possible temperature issues. The temperature could either increase or the temperature could decrease. If it's exothermic and it's giving heat off, I'm going to write heat as a product because it's giving off, like it's being produced. Well, if we increase the temperature, it's like we're adding heat. And heat plus C, it's going to break C apart. And that's what I like to think of it as, is we're adding heat. It's going to make this side of the reaction, the side that has the heat as written down, it's going to make it go the other way. So if we increase the heat, it's going to shift left, and K would decrease. Why would K decrease? Well, if the reaction is truly shifting this way, but the volume's not changing and the moles aren't changing, then we're making more reactants and we're losing products, and therefore K, which is supposed to be a constant, will have fewer products, more reactants, and K will decrease. And we said earlier at the very beginning of this, we said K is a constant unless the temperature is endo or exothermic. Well, here we are. It's not a constant because somebody's changing the temperature. And then we have to go through several logical steps. Let's do those logical steps in reverse. What if the temperature was decreased? If the temperature was decreased, then the heat would be removed. And so you wouldn't have heat plus C pushing in reverse. But the left side could still go forward. Still go forward, still go forward, still go forward, making more products. And so the amount of products would increase. The amount of reactants would decrease. And K would end up being larger. So K would be larger in an exothermic reaction when the temperature is decreased. And then pretty much that whole conversation could be had in reverse. If you change the temperature from exo to endothermic, and the heat, instead of being a product, the heat's over here, and then you have to go through all of those logical steps. And you have to go through the logical steps. Heat's a reactant, I'm removing it, I'm adding it, how would it shift, what would K do as it shifts? It's all little logical steps, but it starts off with what is exothermic, what does endothermic mean, is it producing heat, is it taking in heat, how does that impact when the temperature changes? It's a lot of logic. And then 3A, concentration, which I'm hoping I still have yours. Concentration is directly related to speed. If you increase the concentration, that means you have more particles in there. More particles mean more collisions, so it's just like pressure. It uses an inverse relationship with relation for position, meaning if you add a particle, it's going to shift the other direction. Well, there's evidence that I'm doing this during school. So in case you're at home watching this and you were like, I wish I could hear a bell, there you go. So anyway, concentration, it shifts, it's always going to shift back to K, when you change the concentration. So the idea here is if it was an equilibrium, you have all of this written on there, but just imagine it was back at equilibrium, and then someone adds a lot of particle C. Too much particle C would throw it off of equilibrium. The reaction shifts, the concentration of C decreases, the concentrations of A and B increase to get you back to K, back to that relationship between the products and the reactants. That should be a constant. K is a constant for concentration, K is a constant for pressure, K is a constant for catalyst, K is a constant for moles. The only time K is not a constant, temperature. All right, we're going to wait on this one until the next video.